All right. This would be a lesson for chapter 6.1, followed by another video on 6.2. I hope you guys are good. I miss you guys. It's too bad that we have to continue in this isolation sort of business, but it is what it is. A couple of things you might want to consider before you get started. As you might have noticed through my posts on Google Classroom, every week, I am going to put up your responsibilities for material. It's probably going to be in the form of maybe about 2 sections a week. Whatever resources you need to use, go for it. My videos, go for it. Textbook, go for it. I will be making myself available. For you, it will be Monday because my lessons are supposed to go up for you on Wednesday. So if I were to do a tutorial session on Friday, it might be a little too soon. So I wanted to give you some time to actually work on it and then ask questions afterwards. Occasionally, I am also going to be putting up some formative quizzes and stuff like that so that you can sort of, I guess, build some confidence in whether you can do this on a test or quiz type setting. In terms of this video, you don't want to waste time watching videos like this again and again and again. So bust out a paper and pencil. And as I go through the lesson, you can copy down what I write or copy down, just make some of your own notes that are more efficient so that when you are ready to sort of review previous notes, that you don't watch the videos again. You know that all videos have filler space, wasted time, and that's all precious time for you when you're studying. So take these videos, write down your own notes, and consult your notes afterwards. Don't ever watch this video again, okay? With that said, let's get started. We are on chapter 6.1 and 6.2. This video is going to focus on 6.1, which is just the discrete function section, okay? My purpose for this video is to introduce what the heck a sequence is, because that's going to be talked about a lot in all of chapter 6 and on. And the main biggie idea is how we represent these sequences in different ways. For example, how do we represent sequences in a function notation? How do we represent sequences in formulas, so on and so forth? Okay, without further ado, let's get started. What is a sequence? Long story short, let's get another color going. A sequence is a set of numbers arranged in a particular order. Arranged in a particular order. By definition, that's what it is, but that doesn't really tell you much. So let's do some examples, okay? This is what an example of a sequence is. Here, 1, 3, 5, 7, 9, 11, ... What is the next number? Does that look familiar to you? In grade school, you might have gotten things like this as a kind of puzzle and asked, what's the next number? And the goal was to look at these numbers and develop a pattern. So what's your pattern? What's the next number? The correct answer would be 13. 13 will be the next number in this sequence, a set of numbers arranged in a particular order. So what is this particular order? Take a guess. I'll give you 3 seconds. Some of you might have said, oh, the order is, or the pattern is, every odd number in the natural number world. You would be correct. Some people might have said, no, you start from 1 and you're adding by 2 every single time. You would both be correct. And I'm sure there's a few other ways you can actually express this, but that is in essence a sequence. Here's another one. 2, 4, 8, 16, 32. What's the next number that comes in this sequence? Take a guess? Well, the correct answer would be 64. How do I know? Because in this pattern, I am constantly multiplying by 2. So here is a sequence of numbers that is arranged in a particular order. Sound like fun? Well, how about I throw this one at you? Here's another sequence. Can you guess what the pattern is? Can you guess why these numbers are written in this particular order? What's the next number? The next number would be 7/8. Why? Some of you might say, well, you start at, so the start is 1/2, and then the numerator and the denominator both increase by 1 every single time. You would be correct. Another person might say, hey, no. Whatever the numerator is, okay, so starting with 1, right? Whatever the numerator is, the denominator is the numerator plus 1. So if I add 1 to the numerator, this becomes added by 1 as well. You would also be correct. There's so many different ways you can express it. Last example before I actually get to my point here and then get to the actual lesson. How about this one? Some of you readers out there might actually recognize this. What's the next number? You can pause the video if you want. I'm going to get going in 3, 2, 1. The next number is going to be 89. Wondering how? In this particular sequence, the next number is going to be the sum of the prior two. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13, so on and so forth. This is a very special sequence called the Fibonacci sequence. We're going to come back to this in 6.2, but just thought I'd throw it in there. Okay, so these are sequences. Any questions? Stop right now. You might want to quickly review before we get a little bit more technical here. You ready? To move on into the next part of this lesson, I need to introduce some new vocabulary. First vocab, the word term. Now, the word term you've seen before in polynomials. This is slightly different. In sequences, the definition of a term is a single value or object in a sequence. Okay. So how about we take that second example? Okay, just highlighting this. I'm going to take this example to demonstrate how to use the vocabulary term. Okay, so here we go. My example being, if it was 2, sorry, I should put it in blue, 2, 4, 8, 16, 32, ... In this particular sequence, the first term, so t little 1, let me do that a little bit cleaner because it's the first time you're actually seeing it. T little 1 is equal to 2, because that is the first term in the sequence. The second term, what would that be? 4. The third term, 8. The fourth term, 16, etc., etc. What would be then, just because we already did the fifth term, what would be the sixth term? Right? That is another way of expressing what number that you want without actually having to write the entire thing. Okay? Okay. Well, if that's the case, all of this is to bring us to Tn. In other words, any number. What is Tn? Tn is, in other words, is give me a way to calculate any of these terms in the sequence if I know which term number it is. Can you guess what that formula might be? Well, take a look at the left. Every single time, we're starting with a 2, and every single time we are multiplying by 2. The formula for this sequence would be 2 to the power of n. Does that work? Well, T1 would be 2 to the power of 1. 2. It checks out. T2 is 2 to the power of 2. 4. It checks out. And so T6, in other words, a sixth term, is 2 to the power of 6. Does that check out? You can use your calculators, but I'm going to go on and say yes, it does check out. Okay? What we did here, this thing, what we wrote down here as Tn is something we call the explicit formula of the sequence. That's my next vocabulary. This is the explicit formula of the sequence. Okay. And by definition, I'm going to type this up. It is a formula that represents any term in the sequence by definition. Okay. By that I simply mean relative to the term number. You can't even see that properly, can you? In other words, for the explicit formula, as long as I know what term I want to find, you can calculate that value, right? If I want to know what is the 100th term, right? So using this explicit formula, if I asked you in a test question, what's that? Well, you don't have to multiply by 2 every single time. You can plug it into the formula and tell me whatever that number is. Okay? Yeah, so relative to the term number, so whatever that term number is, you plug that number into the formula and you should be able to tell me what the value is. Okay? Try it. I'll give you an example, okay? Before I actually move on, I'd like you to try this and find, as an example, find the explicit formula for the third example we did. Pause the video now. Give it a shot. Okay? I'm going to trust that you tried it. The explicit formula where Tn would be equal to whatever the term is over whatever the term is plus 1. So if it's the first term, the numerator would be a 1 and the denominator would be the term number plus 1 over 2. If you're looking for the fourth term, the numerator would be 4 and the denominator would be the term number plus 1, which is 4 over 5. Just a different way of expressing it, because as you might imagine, mathematicians being the laziest people in the world, we don't want to write all that. We want to write formulas so that it saves us time and it's efficient. Pause the video give yourself a shot. Why don't you try practicing it with example 1 and maybe even example 4, although that's a bit of a challenge, okay? I'm gonna let you do that on your own time. Before we move on, I need to clear this space. I need to add one more thing to my note so that we would be more than prepared for the questions to come in the textbook. I'm going to go ahead and erase all this. Okay. One last thing I'd like to point out is the difference between sequences as a discrete function versus a continuous function. Okay, so one last thing, sequences. I'm looking at sequences as a discrete function versus a continuous function. Here is what makes a sequence slightly different than just a formula. Okay, so going back to our previous example, 2, 4, 8, 16, 32, so on and so forth. We established that our explicit formula for this sequence is 2 to the power of n. Would you be able to write this as function notation? As a function notation? In other words, if I were to write it as f of n, that would just be 2 to the power of n. That's great. But with the catch. This is what my catch is. What is t1? 2 to the power of 1, which is 2. Good. What is f of 1? 2 to the power of 1, which is 2. Yay. What is t2? 2 to the power of 2, which is 4. What is f of 2? 2 to the power of 2, which is 4. Checks out. Yay! But we get to something funky. What is the 1.5th term? What is the 1.5 term of this? Going once, going twice, surprise, it doesn't exist. There is no 1.5 term in between. It's the first term and the second term. But when we get to a function, is it okay for us to plug in 1.5? Well, what's the problem of plugging in 1.5 into a calculator? Nothing. And if you do, you get 2.828427125, so on and so forth. And that is where we don't agree. A function would assume that any value of n is okay, but that would not agree with the sequence. There is no 1.5th term. And so when we write it as a function notation, you need to be aware that for our domain, in other words, our values of n belongs to a set of real numbers. If you forgot what real numbers is, it's basically the first numbers you learn as a baby. What am I saying real? N belongs to natural numbers. And if you forgot what natural numbers are, they're the numbers that you learn first as a baby. That means it starts from 1 and goes to 2, so on and so forth, all the way to infinity, as high as you can count as a child. It is not a continuous function. Okay? If it was a continuous function, let's put it here, if n belonged to any real number, we would have f of n equals 2 to the power of n as a exponential function. But this belongs to natural numbers. In other words, no decimals are used. It's just 1, not even 0, just 1, and then 2, and then 3, and then 4. So 1 will give me a 2, 2 will give me a 4, 3 will give me an 8, and 4 will give me a 16. And I don't connect these dots. Okay? This would be a continuous function because every single point is connected to it's a connected function. Whereas here, this is what we call a discrete function. Okay, separate points and they are not connected. Just wanted to make that distinction. Please be careful when we talk about sequences. They are discrete functions. They are separated. There is no continuation between 2 and 4. It's just number 2 and then number 4 and then number 8, so on and so forth. Your homework for this section is going to be to try out in page 360, numbers 1 to 3, 5 and 6, 8, 13, and 16. They're going to get you to just go through the motions and like a puzzle, see if you can catch what the pattern is and then express it as an explicit formula. Good luck. If you have any questions, you know where you'd find me. Please email or follow the instructions for the Google Meet. Hope to see you on Monday just to drop in and say hi. If not, or if you're not interested, whatever, work really hard and hope to see you soon.